this example now, we know that the maximum allowable potential difference across a 200 millihenry inductor is 400 volts. You need to raise the current through the inductor from 1 amp to 3 amps. What is the minimum time you should allow for changing the current? So let's start with a list of the things that we know. The inductance is 200 millihenries, so that means that L is 200 times 10 to the minus 3 henries, H for Henry. The maximum potential, delta VL across the inductor, is 400 volts. Any bigger than that and it would burn out. You need to raise the current through the inductor from 1 amp. So your initial current is 1 amp to 3 amps. Your final current is 3 amps. This tells us that our changing current, delta I, is your final current, take away your initial current, gives us 3 amps, take away 1 amp, or a change in current of 2 amps. So we have to increase it by 2 amps. What is the minimum time? We're trying to find the time. So let's write down about what we know for the induced potential across the two ends of an inductor. We know that the induced potential across the ends of inductor is delta V for the inductor is minus L di dt. So change in current over change in time. We don't have a function for current. We have two discrete points. So the change in current over change in time we can write as delta I over delta t. Our current is positive. Our potential, so if we're trying to find the time, we can deal with the absolute values. So our change in potential can be positive or negative. So let's take the absolute values of everything so that we can find what our time is. So the absolute value of the potential is minus L times delta I over delta t. Our delta I is positive, so that means that delta VL equals the magnitude of delta VL, L times delta I over delta t. And if we want to find our delta t is the inductance times the change in current divided by the magnitude of the change in potential. So 200 times 10 to the minus 3 henries times the change in current, 2 amps, divided by the maximum allowable potential difference. Doesn't say which end is higher. We'll put in the magnitude of the potential. 400 volts gives us a time of 0.001 seconds, or 1 millisecond. So that's how much time we have to change it. Okay, let's do another example before we quit this video. Let's say that the current through an inductor, let's say it is given by a function, so it's a little different from the previous example that we just did. The current through an inductor with inductance L is given by current equals some initial value of current, or some maximum value, times sine of omega times t. So our current is changing with some frequency as a sinusoid. Find an expression for the potential difference across the inductor, and from some given values, figure out what is this maximum current. So let's write down what the expression for the potential difference is. Delta V across an inductor is equal to minus L di dt. This time our current is a function, so we'll put in our function. We're able to take a derivative. So minus L d by dt of I0 sine omega t. We can take our I0 out front. The derivative of sine is cosine, and then when we take our derivative, we have to do the chain rule, and we multiply by the derivative of omega t, which is just omega. So that's going to give us minus L times I0 times omega times cosine omega t. So there's the expression for the potential across that inductor. And the minus sign tells us that the potential decreases in the direction of the current. So that's part A. Part B, the maximum potential difference across the inductor is 0.20 volts when L equals what microhenries? I must have forgotten to write that down, sorry. L, the inductance, is 50 microhenries. I'll fill that in right now. L equals 50 microhenries. Sorry. And the frequency F is equal to 500 kilohertz. So let's see how we can use that to figure out what the maximum current is. So our expression for current is minus Li omega cosine omega t. So our potential changes as a function of cosine. Cosine ranges between two values. And the two values it ranges between is minus 1 and plus 1. So cosine has a minimum value of minus 1 and a maximum value of plus 1. So delta VL equals delta V maximum. That happens if your cosine function here is minus 1. And I'm picking minus instead of plus because I want to use this minus 1 to cancel with this minus right here. So if cosine omega t is minus 1, then delta VL maximum equals minus L I0 omega times minus 1 equals plus L times I0 times omega. And here we might remember that omega is angular frequency, which is equal to 2 times pi times f. Now we can solve for that maximum current I0. So I0 is going to be delta VL maximum, the maximum potential across the inductor, divided by L times 2 times pi times f. We can put our numbers in. The maximum potential is 0.2 volts. The inductance L was 50 microhenries. And a micro means times 10 to the minus 6 times 2 pi times the frequency. 500 kilohertz is 500 times 10 to the 3 hertz. And finish up with that in your calculator. You get 0.00127 amps or 1.27 milliamps. Okay, there's one more example I have here. I'll leave that for you to try, but I'll do it and include it with the post-it notes.